Okay, in the last lecture, I have discussed the in vitro cytotoxicity, that is the cell level toxicity, or the potential of the capability of a biomaterial to cause cellular apoptosis, or as well as the mechanism by which cell material interaction takes place. That was largely discussed. Towards the end of the lecture, I also discussed the genotoxicity, that is the toxicity level at the gene level, or in other words, the potential of the biomaterials to cause DNA damage. That was also discussed. Some results were shown to illustrate that how the genotoxicity property of the biomaterial can be evaluated, and to that end the results of the single cell jelly electrophoresis or the COMET assay tests were shown. Now, in continuation with this discussion on the in vitro biocompatibility assessment, in today's lecture I will discuss first the hemocompatibility. Hemo means blood, and blood compatibility testing. What is the basic principle, what is the typical methodology that is taken, and how to assess that whether the blood contacting devices can be hemocompatible, that will be discussed. So, first, blood is considered as a tissue in a sense that blood also contains a large number of cells, and these cells present in the blood as well as number of proteins, and they do perform certain specific functions. The first one is the oxygen carrying capacity, and that gives the viability property. Then antigen specific lymphocytes, that gives the immune capability or immune response. Then white blood cells, the WBCs, that are responsible for the inflammation, and then there are some proteins which helps in the coagulation of the blood tissue. Then other things that are important is the mechanical or material mediated damage to cells. So, this what it meant by that whenever a material experiences some kind of mechanical stress, then that external stress also can cause the damage of the blood tissues. Now, one can do this blood compatibility test both in vitro as well as the in vivo. So, again in vitro means that is the laboratory simulated test, in vivo means that is the experiments which are conducted inside the animal. So, this is kind of more specific information on the hemocompatibility, and this particular biocompatibility test includes determining that both the materials used in the device as well as the device itself, when operated at its maximum conditions, and they should not cause any excessive damage to RBCs or hemolysis. Again, coming to the fact that you have to underline this excessive damage. Now, if you recall the discussion of the genotoxicity, when I have shown you these results, that results, if you go back to the discussion of the genotoxicity, yeah, this is the results of the genotoxicity assay, that is the COMET assay, and these results are expressed in terms of olive tail moment. Olive tail moment means what is the length of the fragmented DNA, and that length depends on what is the eluate concentration. Now, in the x axis eluate concentration, that we have taken just the hydroxyl 20% molite, because we have tested that in vitro and in vivo potential. So, that is the reason that we have selected this particular eluate composition. Now, if you see that compared to the positive control, although these materials, these compositions they have, so compared to the negative control, both these eluate concentrations over greater than 25%, greater than or equal 25%, as well as the positive control, they show statistically significant genotoxic effect, because their damaged DNA damage length or the olive tail moment is much higher. However, that from 25% or more, there that it is much less, OTM values are much less compared to the positive control. If you look at the 5% and 10%, there also the olive tail movement was measured, and then however, they are not that significant compared to the negative control. So, what I am trying to tell here, that it is important to recognize that whenever you put a material or whenever you inject some drugs or some particles inside the human body or in the in vitro conditions, they will cause some damage to the gene level. But your task is to understand that whether the gene level toxicity is very significant or very much statistically significant compared to the control specimen or not. So, in the same way, I was trying to explain here that most of the materials or blood contacting devices or blood contacting materials, they will cause some damage to the RBCs, red blood cells. However, your task is to find out or determine whether this damage is statistically significant compared to some control samples or not. And you cannot have an ideal material which do not cause any damage to the RBCs. So, that is the bottom line I am trying to tell. So, therefore, you have to remember that in a blood contacting device or blood contacting material will have some genotoxic effect, but this should not be statistically very significantly higher compared to what a control specimen or control material they do the damage to the RBCs. So, implant and devices contain materials that are recognized by blood as foreign material. So, what they mention that whenever any synthetic material you are used, be it hydroxyapatite, be it polyethylene or other metals, then they are always recognized by the blood as the foreign material, and therefore, there will be some foreign body response that you can expect. Now, the result is a process of thrombosis often followed by the formation of thromboemboli. So, thrombosis means there will be some blood clotting there at the implant site or at the wound site, and this process generally involves a sequence of protein absorption. Remember, this protein absorption again takes place just like whenever you put a material inside the body, and in case of the blood also contains some proteins. So, therefore, proteins will necessarily be absorbed on the material surface, whether it is a blood or whether it is simple human body plasma. Now, this is what I have already told, that blood is considered as a tissue and that primarily consists of erythrocytes. So, red blood cells, their biological name is erythrocytes, and leukocytes, that is the white blood cells. So, RBCs are generally non-nucleated cells and contains hemoglobin, which allows transport of sufficient oxygen to the tissues. And in how this oxygen is transported, that you know from your basic biology, from school biology, that is oxygen will be attached to the hemoglobin of the RBCs and thereby will be transported to different parts of the body. Now, leukocytes, that encompasses several types of cells, and these leukocytes are the mobile units of the body's protection system, and that is why many times you will see that when you undergo this blood testing, so doctors always tell you to count the RBC and count the WBC. So, WBCs are important for your immune system. Immune means that is actually protection against some external damage or immune system. So, therefore, if the WBCs are very less in your blood, then your immunity is very poor. So, that was the reason that why WBC content is also important. Now, WBC content varies for male and female. So, depending on, you can see that whenever you are writing your sex as male or female, they will give you the particular limit of WBCs that a normal healthy human being should have, and if it is much lower than that limit, then that means it is not desirable. Now, there are also blood platelets, they participate in the blood clotting, and then fourth one is the plasma. Plasma is like a you can consider it as a ECM, extracellular matrix. So, plasma here actually is a fluid component of the blood. So, that means it is a kind of matrix. For any tissue, there will be a matrix where the different cells are aggregated together. So, here for the blood, it is the plasma, that is the fluid component of blood containing various chemicals, enzymes and nutrients. So, these are like essential for the survival of the cells which are contained in blood. Okay. Now, blood, as I said earlier, that blood is responsible for transport of oxygen, nutrients to tissues and the removal of carbon dioxide and waste products from tissues. Now, this cycle is dynamic in nature. This cycle means that is transport of oxygen to the blood and removal of carbon dioxide through blood. That cycle should be continuously operated for a normal healthy human being. Now, many times for the ailing patients or the patients which undergo surgery or who are not healthy, what happens in the blood, oxygen level is reduced and carbon dioxide level is increased, and carbon dioxide level is increased means what? That carbon dioxide is not being able to be transported through the blood, and oxygen level is reduced means that RBCs which carrying the oxygen, they are not performing its normal function, thereby they are not able to supply enough oxygen to the blood, and that is the reason that many of the tissues will die subsequently because of the hypoxia. Hypoxia means that is the absence of sufficient amount of oxygen. Many times if you see doctors or medical professionals, they use the word that patient died because of hypoxia. Hypoxia means that is the absence of sufficient level of oxygen in the blood. The next one, oxygen is bound to hemoglobin within red blood cells, and that increases oxygen transport by 30 to 100 times over dissolvable amounts. So the other ones is the carbon dioxide is dissolved in blood and transported as other chemical compounds after reacting with blood constituents. So all this oxygen also directly bound to the hemoglobin, and that is the way oxygen is transported. Similarly, carbon dioxide also is dissolved in the blood. Blood means it is the blood plasma, and then transported as other chemical compounds after reacting with blood constituents. And nutrients are dissolved directly in the blood and often in combination with other chemical structures. Now this is your blood elements. Blood elements means you have the proteins, then you have the WBC, then you have the RBC, and you have the plasma, right? These are like 4 major elements of the blood. Now you have the erythrocytes, you have the leukocytes, you have the proteins, you have the plasma. Now when a material will react with blood, blood means it is a combination of all these. So therefore the material will be reacting, interacting with all these molecules. And what will happen initially, like as you know from your basic cell material interaction, the proteins will be absorbed first on the material surface, and these proteins will be different type, that is the blood proteins, and this will be different type when in other cases simple, that when a bone replacement materials are implanted at certain specific anatomical location. Now there can be 3 types of reactions. One is the non-thrombogenic or pseudo intima. Non-thrombogenic means there is no thrombus formation. I will come to this, I will show you some slides to show you, illustrate that what is called thrombus. Now that it is a non-thrombogenic means it is very good, like there is no blood clotting, that coagulation of the blood cells does not take place, and therefore it is very good, that is like desirable. Then it can be thrombogenic and adherent. Thrombogenic and adherent means you have the thrombus formation, and this thrombus will be adhering to the biomaterial surface. Third one is the thrombogenic and non-adherent. Thrombogenic and non-adherent means thrombus will be formed, but as the blood flow will be continuously, it is in dynamic conditions, so the subsequent blood flow will take away all the thrombus, so therefore it is non-adherent. So this is that effects of the blood flow on the material surface property on platelet transport and reaction with surfaces. Now what you see that blood flow, so essentially the blood flow you can consider that it is a plasma, and inside the plasma you have all these leukocytes or RBCs or WBCs, they are there, this is the blood cells. And then what will happen, these blood cells initially will be adhering, and first will be the protein absorbed, and then after this protein absorbed, then blood cells will be adhering. They can spread on the surface like the way normal cells, like fibroblast cells, osteoblast cells, they spread on the surface. Now here is what actually I thought I will first show you, so that you understand that what is thrombus and what are the different reactions those are possible. Now these are like test device. Test device means this is your biomaterial. Okay. Now in this biomaterial, now this is a cylindrical type of object, you can see. So this blood is made to flow at a constant rate through this device. So that means continuously this biomaterial is in contact with the blood cells, blood proteins, everything, blood plasma. Now if a biomaterial is strictly hemocompatible, like excellent hemocompatible material, then this is the most desirable situation. There is no thrombus formation at all. Now when a biomaterial is non-hemocompatible, that what you see is that thrombogenic, or this causes thrombus formation. Thrombus means that is the aggregate formation of the blood cells, and it will be combined with the blood proteins, then form a, this is like individual thrombus formation. And then large thrombus forms, then other scenario is that there is a thrombus form, and this thrombus is getting transported. That means this thrombus is not strong enough to sustain the subsequent blood flow, because blood is flowing continuously, and if the thrombus is not strong enough or is not strongly adhering to the biomaterial surface, then the blood will immediately take it out from the material. And then fourth one is that it is highly reactive toward blood, but deposited material removed through lysis. Cell lysis take place, and therefore it is blood cells are adhering, but they do not form large thrombus, and then blood cells also undergoing cell lysis. So that means it is not non-hemocompatible to that extent like this way. So this is like cross, this is like okay, you can have it, this is like, you know, it is like very mild cross, it is not like very strong cross like this one, okay. And the most desirable is that no thrombus formation takes place at any given time during exposure with the blood. So I hope this is clear to you, that you know what is meant by blood material interaction and hemocompatibility assessment. Now this actually tells you that you know how to select that hemocompatible material. Now there are two materials that are shown. One is that CP titanium. CP means commercially pure titanium. Second one is that commercially pure titanium plus DLC is coating. DLC stands for diamond like carbon. So that means that diamond like carbon is coated on the titanium surface, but your base surface is the same titanium, and that is possible because all this cell material interaction, blood material interaction is essentially surface property driven. That means it is the surface property that is important in this all these interactions, right, biological interactions. So therefore if you can manipulate the surface properties, or if you can manipulate the surface composition, then also you can induce the good biocompatibility property, although your underlying substrate can be non biocompatible. You understand what I am saying? So the same thing has been shown here, that if you have the commercially pure titanium, you see that these are like thrombus here, right, okay. And then if you have the DLC coating, then the thrombus formation is also taking place, but if you see that extent or the quantification of this thrombus formation, it is largely non-desirable, whether this can be tolerated or this can be managed. If you take a control sample and then put the same treatment of this in vivo biocompatibility test, you will probably see the same control sample will have some kind of thrombus formation, but not to that extent. So statistically, if you quantify this versus this control versus CP titanium plus DLC coating, you will see this will not be statistically significant in that sense. So therefore you can consider it for potential blood conducting device application, right. So this is like, you know, some examples that I have taken from literature, that is, you know, platelet consumption when exposed to blood for 30-minute duration. Now you can see when you want to compare the efficiency, or if you want to compare the blood compatibility properties of the different materials, then you have to keep all other parameters constant, and all other parameters means test duration, blood flow rate. So blood flow rate should be constant. Test duration here it is taken as 30-minute duration. Now after 30-minute duration, what you see here, Ti6Al4V, that means titanium 6% aluminum 4% vanadium, ultra high molecular polyethylene, that is UHMWP, that ultra high molecular polyethylene, that is an example of a biopolymer. Commercial pure titanium, that is the third one I have shown you the previous slide. Commercially pure titanium plus DLC coating, that is diamond like carbon coatings, and titanium 6Al4V plus titanium nitride coating. So you have this diamond like carbon coating, you have this titanium nitride coating, and those two coatings, as you can see here, that they are the mean value, if you consider this mean value is much less from this titanium 6% aluminum 4 vanadium, or even the ultra high molecular polyethylene. But since that error bars they overlap, I don't think that they have very much statistically significant reduction by putting this coating. However, if you consider that overall blood compatibility of these materials, you can clearly see because of the presence of titanium nitride coating on Ti6Al4V. So if you compare this versus this, then you can put a star. Star means that is statistically significant. But however, this versus this, I don't think it will be statistically significant because their error bars almost like overlap with each other. Now, this is the WBC consumption, that is the white blood cells. So, after exposure to blood for 30 minutes duration, you can count that how many WBCs or white blood cells are present on these blood contacting devices. Again, what you see that all these error bars, they overlap with each other. That means, as far as the WBC consumption is concerned, there is no statistically different result that we can obtain, statistically significantly different result that you can obtain among this particular group of materials for this particular combination of test parameters. Okay. This is the example of this artificial art valve, which is made of this titanium 6 aluminum 4 vanadium, that is the alloy, plus titanium nitride coating, and you can see that is that after the 192 days, means it is roughly around 28 weeks, right. So, 28 weeks means it is roughly around 7 months. So, it was implanted in some animals, and this duration of this implant is 7 months, and then here it is one around the same time. So, we are comparing with that titanium nitride coating and without titanium nitride coating, and this is like after valve is explanted after 6 months, and then what you can see roughly that this material, they have a much better performance compared to the other material. So, after I completed this in vitro or in vivo hemocompatibility, that is blood contacting for blood contacting devices, I will now discuss with you that corrosion and wear of materials in biological environment. Now, corrosion and wear are these properties which are important for mostly for metallic materials, because metals are largely prone to corrosion in the in vitro environment or in the simulated body fluid environment. So, where is that progressive material damage at the two surfaces in relative motion, that is the definition of the wear. I will come to this later. Now, that is why I have made this statement here, this is critical for metallic implant like stainless steel, titanium. Now, why stainless steel are getting replaced by titanium, although titanium is expensive, because titanium has much more or better corrosion resistant compared to titanium. Titanium has better corrosion resistance than stainless steel, because titanium shows active passive behavior. I will show you all those things than stainless steel. And wear resistance wise also, metallic materials, they have lower hardness, and therefore these metallic materials, they have higher wear rate. Now, wet corrosion behavior is what is important for metallic materials. Wet corrosion means, for example, this is abraded iron, that is that iron or iron based steel materials. Now, iron can be oxidized to form Fe+2 ions, and then oxygen, that is aerated water, then oxygen can form dissolved oxygen in the water can form OH minus, and Fe+2 can react with the OH minus to form iron hydroxide. So, that is the way iron will be continuously leached out from the metals, and that is the kind of corrosion mechanism by which that iron will be corroded in aerated water. Then surface degradation, this is the attack on these metals which is much faster than for dry oxidation. Now, dry oxidation means that is the corrosion which takes place in the absence of any water, that means in the ambient conditions. Now, if the oxide is insoluble, the deposition may occur away from the surface, and if the deposition of the surface does not occur, the layer formed may be relatively loose, giving the protection to further oxidation. Now, these are more relevant to the dry oxidation, and dry oxidation does not take place in case of the application of the biomaterials. Now, let us see that what is Pourbaix diagram. Pourbaix diagram means that is E versus pH diagram. So, other name of Pourbaix diagram is a E versus pH diagram. Now, inside the human body or the simulated body fluid, their pH is always maintained at 7.4, and inside the human body your core pH or the blood pH is a 7.4. That is the reason why all the in vitro experiments, they are conducted at pH is equal to 7.4. Now, inside the human body, depending on the concentration of the ions, then this E value, that is the electrochemical potential value, they also vary over a large range. And what you can see, that is given for the example of chromium, for example, because stainless steel, the stainless, that corrosion resistance of the stainless steel is imparted by the presence of chromium only, because stainless steel means that is iron plus carbon, that is always, that steel means that is the solid source of iron and carbon. If carbon is not there, you cannot call it steel. And stainless steel means at least 10.5% chromium must be there, and this is the chromium which gives the steel the required corrosion resistance properties. So therefore it is important to find out that what is the stability of chromium, for example in pure water, as far as the Pourbaix diagram is concerned. That is the reason that why I am showing that Pourbaix diagram of the chromium. Now what you see here, that at around 7.4 here, this is the line, if I can draw, at pH is equal to 7.4. Now what you see, if the electrochemical voltage is highly negative, and then it is in the immunity region. Immunity means, that means the stainless steel will not undergo any corrosion, that means stainless steel will be immune to corrosion. Okay? So that means the surrounding environment will not have any corroding effect on the chromium. Now the moment this is electrochemical voltage at this 7.8 is above around minus 1.2 or minus 1 or up to this value, that is around 0.6 or so, then it will undergo passivation. Passivation means what? That means chromium will form chromium oxide, or chromium can form other higher oxides also, I mean depending on what is the voltage and what is the conditions. So passivation is still okay, immunity is the highly desirable, so I am putting is 2 tick. Passivation is also desirable, that means that chromium is protecting underlying material by the forming the passivated oxides on the surface. Now the moment this electrochemical potential at pH equal to 7.4 is above 0.8 volt, then your corrosion starts. So at higher electrochemical potential range, although there is sufficient amount of chromium which otherwise gives you good corrosion resistance, that will not serve its purpose. Okay? So therefore in the human, the message that I am trying to give from this slide is that inside the in vivo conditions, or in vivo or inside the human body, even if you put the stainless steel, it will not protect you from corrosion if the electrochemical potential value is 1 volt or more than 1 volt. Okay? So then the stainless steel itself will undergo corrosion. The other things that I want to tell, that here all these experiments, all these data points based on you are identifying whether it's the immunity region, passivation region, corrosion region, they are based on experiments in water. But your simulated body fluid is not a pure aqueous environment. It contains several salts like sodium chloride, calcium chloride, etc., potassium chloride. And if you want to simulate closely the in vivo condition, then it also contains the protein molecules like serum protein and so on. So there the environmental effect, because of the presence of the sodium chloride and all, there the environmental effect will be much more significant than pure aqueous environment. And again it may be so that your passivity region is reduced or is contracted, and therefore with simple increase in the above 0 volt, the material can go to the corrosion region. Okay? So in that kind of SVF environment or in vivo environment, this particular diagram will not be valid anymore, and you need to construct a separate diagram by conducting tests in the pure SVF environment or the body environment simulated, the solution which will simulate very closely the in vivo environment. Okay? And as I said, that knowing the concentration of the SVF or knowing the concentration of the different elements in the in vivo environment, the corrosion region will be expanded much more. Expanded much more means their passivity region will be narrow and corrosion region will be expanded much more, so that this material can be easily corroded in that kind of environment. Now coming to the tribology, that is the friction and wear kind of test. So this tribology is derived from the Greek word tribos, that is means rubbing. Rubbing means when two materials they rub against each other, so that is at the interface these materials will undergo surface damage, and surface damage induces the material removal, and that can cause the friction and the wear of the material. And it is defined as the science and technology, so this is the formal definition, is defined as the science and technology of interacting surfaces in relative motion. Important thing of tribology is say system dependent property. System dependent property means tribological properties, it depends on the material parameters and at the same time it depends on the operating parameters. Now if somebody will ask you that what is the coefficient of friction of steel, it does not mean anything, because coefficient of friction of steel against steel would be different for coefficient of friction of steel against alumina or against zirconia. So if the other body or the matting body or the counter body is different, then coefficient of friction will also change. So therefore if you make any statement that coefficient of friction of steel is 0.5, it is scientifically wrong, it is meaningless statement. You have to always tell coefficient of friction of steel against what, that material also you have to explicitly mention whenever you mention the tribological property. Okay. The second thing is that operating parameters mean that is tribological properties are also dependent on the sliding speed, it depends on the load. So if you change your load or if you change your sliding speed or the fretting speed, then tribological properties also will be different. Now come back to the same system, let us say steel versus steel. If you change the load from 5 Newton to 10 Newton, then your friction coefficient also will change, your wear rate also will change. If your sliding velocity is changed from 1 meter per second to 4 meter per second, then all the tribological properties also will change, because the moment you change the operating parameters, tribological properties will change. The moment you change your counter body or your matting couple, then also tribological properties will change. Now it encompasses the study of friction, wear and lubrication, and lubrication is mostly related to the mechanical engineer, so we will not be dealing with lubrication here as far as the biomaterials are concerned. Now what is meant by system property here? Suppose this is a one body A, this is another body B, so these are like two matting couple. Now if B is different, if B is replaced by C, then your tribological properties also will be changed. The other things that I am trying to mention here is that although this both the A and B, if you look at your own eye or naked eyes, then you will find that they are like perfectly smooth surface, but microscopically they are not smooth. They always contain this kind of hills and valleys, which in scientifically known as asperity. So this is one asperity, and then the other asperity is, for example, this or this. So each surface contains capital N number of asperities, whether it is a flat body or whether it is a ball surface. Now tribological interaction actually take place in these asperities and asperities. Whenever you will put a load here P, then B will make contact with A only at the multiple asperities, not all throughout the surface. So therefore whatever friction coefficient or whatever wear you see, that is the result of this physico-mechanical interaction between the n number of asperities from the two opposing or two matting solids. So this shows that friction coefficient under different tribological conditions for self-mated steel. Now typically friction in a vacuum, that can be very high, that can go up to 10 or so. Dry friction, now classical metals or specific metals, it can vary from 0.1 to 0.8 or 0.05 to 0.3. Lubricated friction, then it values between 0.05 to 0.8 and 0.02 to 0.3. Now this is the initial and sliding coefficient of friction. Here you can have different materials for tribological applications. For example, you can see cobalt chromium. This is used as that cobalt chrome moly. These are used in the knee joint applications. And in the knee joint applications, if you see in the dry conditions, that means without any lubricant, it is around 0.55. So 0.6 is the coefficient of friction. The moment you give the lubricants like serum or synovial fluid or albumin, that is the solution in the protein solution, in the presence of the serum protein and all, tribological properties fission coefficient is reduced to around 0.1 or so. In the cobalt chrome moly versus polyethylene in serum solution it is 0.08. Now alumina versus alumina in Ringer solution it is somewhere around 0.1 to 0.05. So as you see that if your solution is changed or if your environment is changed, then your coefficient of friction also changed. Now if you look at the what are the different factors which will influence the tribological behavior. First one is that contact geometry, whether it's a ball on flat, whether it's a ball on flat type of geometry or whether it's a pin on dish type of geometry, that is important. Then materials in contact, as I said, the tribology depends on the material parameter as well as operating parameter. So the moment you change the matting solid, that is that other material which is in contact with the nominal material, the tribological properties will also change. Now like biological properties, tribological properties are also surface sensitive. That means underlying substrate can be same, but if you do any surface treatment or if you put any coating on the material surface, then tribological properties also will be influenced or also will be changed. For example, you can put titanium, but the moment you put titanium nitride coating on the same titanium, then the tribological properties will change, because then tribological properties will be determined by the properties of the titanium nitride, not the titanium. Then roughness of the tribological surface. So if you remember that what I have shown you some 2 slides back, that is any nominally flat surface always composed of multiple number of asperities. Asperities means like those are like hills and valleys, those are present in the material surface, and these asperities actually will interact at the loaded tribo contact, and that leads to the friction and wear of the system. Fourth or fifth one is the normal force, that is the normal force, that is Fn, that is applied through, on the matting couple. This depending on the normal load, then that will form some Hertzian contact diameter, and you can find out that what is the Hertzian contact pressure at the tribo couple, what is the time duration, and what is the total sliding distance, what is the sliding speed, what is the ambient or test temperature, and atmosphere and lubrication. These are all called the operating parameters. Operating parameters means like this is the load, what is the sliding distance, what is the sliding speed, etc., and as well as the atmosphere. Now what are the different mechanisms of the wear can be classified as the 5 primarily distinguishable mechanisms. That is, one is that abrasive wear, then it's called adhesive wear, then oxidative wear, then erosive wear, and the last one is the fretting wear. Now for any given technological applications, it is important that not a single but a combination of wear mechanisms might operate. That means it may be so that abrasive wear is dominant, but you have some contribution from the adhesive wear, right? At the same time, it may be so your oxidative wear is the dominant wear mechanism, but you have some contribution from abrasive wear. That means there will be always some dominant contribution of particular wear mechanism. In addition to that, you also have minor or noticeable contribution from the other wear mechanism. So you cannot say that for this particular operating combinations, operating parameters, and for this particular sliding couple, it is only abrasive wear that takes place. Okay, so it is a combination of mechanism that takes. Now abrasive wear means like you have a sharp asperities, and then sharp asperities is actually abrading the material. The other time, many times people also describe abrasive wear is like a ploughing mechanism. Ploughing means, if you remember, the farmers, they plough the ground. Plough means like they take out that mud or they dig the mud, and then that helps in the agriculture. So similar things, what happens in the abrasive wear, it is a conical asperity, if you can notice here, and then conical asperity, it abrades away the material and it forms the chips kind of thing. These chips are formed also during the machining of the materials. Now this is the called two body abrasion. Two body abrasion means this is body number 1, this is the body number 2. Now what is called three body abrasion? You have this body number 1, this is called body number 2, this is called body number 2, and this is called body number 3. Now what happens in some abrasive wear, you have this wear particles that is generated. Wear particles means now whenever the material will undergo extensive damage, then some part of this material either from body 1 or either from body 2 they form some kind of wear fragments, like wear materials, like removed materials, and these wear particles is called body 3. Now, in the loaded contact, in this kind of situation, when one body is moving with respect to the another body, or one body is in relative motion with respect to the other body, then this is the wear particles which will contribute to the friction and wear. And these wear particles are typically hard abrasive particles, and these hard abrasive particles either can be intentionally introduced between the two bodies, or they can be self generated during the wear experiments itself. This is little bit more of the abrasive wear mechanisms. This is called two body wear, and this is called three body wear. As you can see here, this is the wear fragments they form, and this is the chips that can be removed immediately during the next impact. Now, the second three body wear is that it is that external wear particles which are introduced in between the two fast bodies. So, two fast bodies means this is body 1, this is body 2, and this is the third body, but here these wear fragments is generated in situ, but here these wear fragments or these wear particles or these abrasive particles are introduced externally at the interface between the two fast bodies. This is the another wear mechanism is called adhesive wear. Adhesive wear means that essentially when the two fast bodies 1 and 2 are made of the same material, for example copper versus copper or iron versus iron, in that case you have the adhesive wear, and the adhesive wear means they can initially make welded joint. You know the welding means when the two materials are joined together. So, similar things happens because they have the same composition, as I said, like copper versus copper or iron versus iron. When they have the two same composition, that welding can take place very easily. Then what will happen when this one body is in relative motion against another body? That relative motion can only take place if this welded joint can be broken as a wear fragment, and that is what has been shown here. So, formation and subsequent shearing of welded junctions between two sliding surfaces, that what takes place during the adhesive wear. So, this slide shows actually that different contact configuration, what you can achieve in different test setup. This first one is called pin on disc type of setup, and this pin on disc is most widely used across the world, and essentially as the name suggests that pin means this is your cylindrical pin, and this cylindrical pin is forced against a rotating disc. So, normally here as I said that one body is in relative motion against the other. So, here the rotating body is number 1 and pin is number 2. So, disc always rotates at a certain rotational speed and pin stays at rest at a particular position. Okay. So, after that what will happen? You will find is a wear track is formed. Wear track means this track experiences the material damage, or this track is that area where the material damage and the wear has taken place. Okay. Then you can find out if it is a metals which undergoes extensive wear, then if you can measure the weight before the test, you can measure the weight after the test, then you can find out that what is the mass removal due to the wear test. In ceramics, that wear volume is much less. Then what you do after you do this test, then you can take at different position the 2D surface profiles using the non-contact surface profilometer like laser surface profilometer. Then you can measure the area of this profilometer, each profile, and then you can put this profile, the area as a function of the distance, and this will give you this kind of curve. You can integrate the under the curve, that will give you the volume of the wear curve. So, this volume is the wear rate, essentially it tells you the wear rate. Now, this B is known as the pin on cylinder type of configuration. Pin on cylinder means again it is a rotating cylinder, and this rotates at a certain particular speed, and the pin is stationary, and this pin actually also experiences wear. The third one is that a unidirectional test. Unidirectional test means it is not a that rotating type of motion, but it is a linear motion, and linear motion that it always takes place in particular direction. The fourth one is that 4-ball test. 4-ball test means this is one ball, this is the other 3 balls, and this ball is in the loaded contact against the 3 balls, and it rotates, then it causes the friction and wear. Now, since I have discussed so much on the scientific aspects of the what is the wear mechanisms, or what is the friction coefficient of the different materials, what are the factors which influences the friction and wear properties. I would like to now give you an example or one important example where wear causes significant damage of the biomaterials. Now this example is taken from the total hip joint replacement THR. This is one of the orthopedic applications. Now this is your stem. Now this stem can be made up of titanium or stainless steel. Titanium is expensive, is very costly. Stainless steel is rather cheap. In developing nations like India, people always use the stainless steel because people cannot afford that costly titanium stem. However, titanium, as you know, has much better corrosion resistance than the stainless steel. Therefore, if you use the titanium stem, then it will have a much longer life compared to that of the stainless steel. Or durability or longer life lasting is much better for titanium compared to stainless steel. Now this is your femoral ball head. Now this is your femoral ball, and this femoral ball can be made up of either metal, stainless steel, or it can be made up of ceramic like alumina or zirconia. And then this is your acetabular cup, and this acetabular cup is typically made up of ultra high molecular with polyethylene, or it can be some ceramic surfaces also. But what I am trying to focus on here, that the wear takes place here primarily here because this ball has to be fitted inside the acetabular cup, and during this motion, that human motion, what happens, this ball and the acetabular cup surface will always make some kind of reciprocatory motion or the fretting kind of conditions. So that is the reason whenever you want to replace this ball material and replace this ultra high molecular polyethylene cup, you must do wear test in the simulated body fluid environment before you can approve that this material will have a longer life or better biocompatibility property. So as I said in the beginning, biocompatibility is a broad term. It encompasses cell toxicity, it encompasses genotoxicity, it encompasses the hemocompatibility, friction, wear, corrosion, all these properties, but it should be either in the in vitro environment or in vivo environment. Then only you can call it as a biocompatibility property.